Okay, so we live in a world that is just drowning in data, right? But so much of that data is messy, it's incomplete, it's uncertain. So, how do we build intelligent systems that can actually make sense of it all? Well, today we're going to dive into a really powerful mathematical answer to that exact question.
I mean, this is the fundamental challenge, isn't it? Think about a doctor trying to make a diagnosis with only half the symptoms, or a bank trying to predict market trends. The information is almost never perfect. So how on earth do you write code and create rules when the data itself is, for lack of a better word, blurry? Turns out, the answer actually starts with how we think.
So, before we get into all the really cool math, we need to get our heads around a super simple, very human idea. Our brains are absolute masters at thinking in chunks, or as computer scientists like to call them, granules. Just think about it for a sec. When you look at a photo, you don't register millions of individual pixels one by one, right? No way. You see a face, you see a building, you see a cat. Your brain automatically groups those pixels into meaningful granules. It's kind of like playing with Lego. You don't see all the tiny little plastic dots. You see the bricks, and you see the spaceship you can build with them. This chunking is absolutely key. And that's where this bigger idea comes in, granular computing. This is a whole field of study that's all about designing computer systems that think the same way, by grouping similar things into these granules to tackle really complex problems. And rough set theory, which is our main event today, is one of the foundational tools in this entire paradigm. So, the big question is, how do we actually create these useful granules from a pile of raw, messy data? Well, let's zoom in on one of the most powerful mathematical tools for doing just that. Meet rough set theory. Now, this was developed way back in the 80s by a Polish mathematician named Zdzisław Pawlak. And its genius is that it doesn't try to find one single perfectly clean answer in messy data. Instead, it fully embraces the uncertainty and learns how to work with it. Okay, picture this. You're trying to describe a big, blurry cloud in the sky. You can't just draw one perfect, crisp line around it, can you? It's impossible. But what you can do is draw two lines. One line way on the inside that captures the dense part you are absolutely sure is the cloud. And then another, bigger line on the outside that contains everything that might possibly be part of that same cloud. That's exactly what rough set theory does, but with data points. The first of these sets is called the lower approximation. This is the no doubt about it, 100% certain core. So, if we're trying to identify good credit risks, this group would only have the people we are absolutely confident about. This is our zone of certainty. And the second set is the upper approximation. This is our could-be boundary. It includes all the definite yeses from the lower approximation, plus anyone who might possibly fit our definition. We're casting a much wider net here to make sure we capture all the potential candidates. So you've got this beautiful contrast, right? On one hand, you have certainty, what you know for sure. And on the other, you have possibility, what it could be. The lower approximation gives us that guaranteed positive region, while the upper approximation gives us that possibly positive region. And together, they create this amazing map of what we know for sure and what we don't. And here's where it gets really cool. By defining our blurry concept with these two precise boundaries, we automatically slice our entire universe of data into three incredibly useful and distinct regions. First up, you've got the positive region. These are the items we can classify with total confidence. They are definitely 100% in the set we're looking at. Then you have the negative region. This is everything that falls outside of even our widest boundary, the upper approximation. So we can say with just as much certainty that these items are definitely out. And finally, we get to the most interesting part of all, the boundary region. This is the space between our certain in and our potential in. It's the blur itself. And this is the real power of rough sets. They don't just ignore uncertainty, they precisely identify it, they measure it, and they put a box right around it. Now, this all sounds fantastic, but how do we know this whole system is mathematically sound? How can we trust it? Well, that's where the axiomatic part of the name comes into play. You can think of axioms as the laws of physics for a mathematical system. They're the basic, fundamental truths that everything else is built on top of. They give you a logical blueprint that guarantees the whole structure is consistent, reliable, and isn't just going to fall apart. So, this axiomatic approach lets us do something really clever. It lets us solve the reverse problem. We can start with just a pair of abstract concepts. Then we check if they follow the rules, if they satisfy the axioms, and if they do, we get a mathematical guarantee that a real, valid, underlying data structure must exist. It's like checking the blueprint for a skyscraper. If it follows all the rules of engineering, you know for a fact a stable building can be built from it.
And that right there is the core promise. This formal guarantee is what makes the whole theory so incredibly robust. It's not just some handy trick. It's a logically sound framework that gives us real confidence in the knowledge we're pulling from our data.
And because we have this super solid axiom-based foundation, the theory doesn't have to stop there. We can actually extend it to build even more powerful tools to handle all different kinds of uncertainty.
So the original theory was a little rigid. It needed data to fit into these neat, separate boxes. But then came generalized rough sets, which are way more adaptable. They can handle more complex relationships and even overlapping groups. You know, like a movie that could be both a comedy and an action film. Generalized RST is built for that messy, real-world complexity.
We can even create hybrids. There's another tool called fuzzy set theory that deals with vagueness, things that are a matter of degree, like how tall a person is or how hot a day is. When you combine that with rough set theory, which handles incompleteness, you get the best of both worlds. So rough sets can tell you, is it in the group? Yes, no, or maybe. Well, fuzzy sets can answer, okay, but how much is it in the group on a scale from 0 to 100%? So let's zoom all the way back out and tie all these powerful mathematical ideas back to where we started this whole conversation.
And here it is, the whole sophisticated machine, the lower and upper approximations, the boundary regions, the axiomatic guarantees. At its heart, it's all a formal, powerful, and reliable way to do granular computing. It's a method for teaching our computers to see the world in meaningful chunks just like we do. And that leaves us with a really fascinating final question. We're living in this age of big data, but big data is also really messy data. So maybe the key to building truly intelligent artificial intelligence isn't just about processing more information faster. Maybe it's about building systems that can fundamentally understand, quantify, and reason with the uncertainty that is just baked into the real world. Perhaps these rules of uncertainty are the very foundation we've been looking for.